Hello, geology enthusiasts. We're back for another exciting episode of Geologic Time. So grab your caffeinated beverage and let's get started. Today, we are going to focus on the Silurian period. But before we do that, I want to review where we've been so that we have a trajectory to know where we are going. So you will remember from our last lecture that we talked about the Ordovician. And at the start of the Ordovician, we saw one of the highest overall sea levels ever recorded on Walter's worldwide sea level curve. And so we said that that sea level was more than 400 meters higher than it is at modern day. And so we're thinking about a globe that is just about completely submerged in water. And so the land masses that were present, the original craton, that original bedrock, were submerged with shallow marine environments. And so the benefit of that leading out of the Cambrian and the Cambrian explosion was that we formed Kingdom Anomalia and the Metazoans. And so now we have these elaborate and extensive ecological niches that are going to be home for many of the phylums that we see uprising in the Ordovician record. Additionally, when we think of terms of Pangea, we are focusing on Gondwana land being at the southern end of the globe. So the only thing that is near the equator is really Laurentia, North America, and Eurasia, and then the globe is heavy at the southern end of the hemisphere, and that's going to prove to be really important. So the phylums that we see uprising in the Ordovician include Phylum Bryozoa. We said that those were colonial organisms, and we talked about them being tabulate, rugozid, or encrusting. Bryozoans are related to brachiopods. Both are sessile, so they're both rooted. The next is Phylum Echinodermata, and that helped us to introduce more soft-bodied organisms, and those soft-bodied organisms had some mobility based on the movement of the water column. They also had new protective features like being able to sting, and they could be carnivorous in that aspect too. So not that they were intentionally searching for food, but they had a mechanism which could help them to have a food source, like the stinging tentacles, for example. The next is Cnidaria. And then within Phylum Mollusca that we saw previously uprise in the Cambrian, we've expanded on that with different phyla, and that includes Phylum Gastropoda. So we saw little gastropods, and those are also scavengers, and they're scavengers, predators, and they're mobile. And when we see the increase in gastropods, we also see the decrease of stromatolites. So they're harvesting on those tidal marine environments. And then probably the most exciting event of the Ordovician was the explosion of Phylum Mollusca to produce Nanolodia. And so Nanolodia will finish and complete the food web. Nanolodia will be a top predator. It's going to have a large brain cavity. It's going to have eyesight. It's going to be a true predator. And that makes a whole lot of sense because when we look at the Ordovician environment, there is a lot for him to harvest on. Because we developed this top predator of Nanolodia, we're going to see trilobite expand with different body parts to protect them. So his ectoskeleton is going to get a little bit more in defense mechanism mode. So we developed the food web all the way up from the bottom all the way up. So we see Kingdom Monera, Kingdom Protista, and Kingdom Anomalia present within that food web in the Ordovician. Unfortunately, all good things have to come to an end, and so we end the Ordovician in a mass extinction. And a mass extinction means that at least 80% of all life on the planet will die rapidly. For the Ordovician extinction, we see it happen in two specific waves. The first one relates to the sea levels decreasing, and as sea levels decrease, producing a regressive boundary, those shallow marine environments where all these phyla live becomes exposed above surface. So remembering that most of them are sessile, so they don't have the mobility to move, so they're going to die instantly. And also because this Ordovician glaciation was initiated by a glacial phase. We see the waters become much colder, and they become colder quickly, and colder water can hold more carbon dioxide. So you end up choking off the life that is actually living there. And as a result, we see the extinction of Nanolodia. We see half the phyla of brachiopods and half the phyla of rhizomes go extinct. So the other half will rebound. Trilobite makes it through, fortunately, and the other 20% of life on the planet will make it through. But we've ended in the glaciation, and you can ask the question, well, what caused the Ordovician glaciation? And you'll remember that one of those large controls on global climate has to do with the position of those continents. And so in this case, those land masses are heavy towards the southern end of the globe, and so they're being completely circled by cold water. And so once you initially get the glacial sheet to grow, you end up with a positive feedback cycle called the albedo effect. So that white ice sheet reflects heat, causing the climate to cool, causing the ice sheet to grow, reflecting more heat, etc. So it was a sad day at the end of the mass extinction, at the end of the last lecture. But, you know, life renews itself. And that's the theme that we're going to find over geologic time. So we're going to move into the Silurian. And here in the Silurian, we are thinking about how the planet is beginning to warm. And so some of the questions are, well, what causes that ice sheet to melt, right? Because that's the thing. Like once you grow an ice sheet, how do you turn off the cold? And in this case, remember that that all the plates are trying to make it towards the equator. So we're forming a Pangea. So it just took a few degrees of a latitude shift in Gondwanaland to move north to cause the ice sheet to begin to melt. Additionally, when you have a glacial phase, remember that you have the grinding of bedrock underneath. And so we have transgressive boundaries exposing land above sea level. So what can also happen is that any of that stored carbon dioxide that was beneath the glacier gets released. And that's one of the concerns that we have today, is that once you start to have melting, you have carbon dioxide that begins to release. So it's either stored in the bedrock itself, or it's stored beneath the glacier. So you have these pulses of carbon dioxide that go into the atmosphere, and we know carbon dioxide is a greenhouse gas. So we quickly transition out of that Ordovician glacial phase. I want to remind you too that the Ordovician mass extinction was the second largest on record. We're going to talk about 5 different mass extinctions in this class, and that was the second largest. So here we are in the Silurian, and the planet is going to quickly warm. And so some of those shallow marine environments are going to begin to return. We can see our map of where the plates are, and you'll notice that Gondwanaland and more of the land masses are shifting more towards the equator. So there's a slow and steady increase in sea level. So my question to you at home viewers is, what's going to happen next? Do you know? What's going to happen? What's going to happen? Exciting in the Silurian. Coming out of that glacial phase, slow rise of sea level means that for the very first time in geologic history, we have a landmass that's exposed above the Earth's surface. So prior to the Silurian, the majority of the globe, the vast majority of the globe, was completely submerged underwater, and certainly during the Ordovician. So after that last glacial phase, you now have land exposed, and because you have land exposed, you're now going to be able to develop our last 2 kingdoms. So in the Silurian, for the very first time, we see the uprising of kingdom fungi and eventually kingdom Plantae. So I want to remind you that when we talked about the kingdoms in the order of complexity, we said kingdom Monera, Protista, fungi, Plantae, Animalia. But listed in order of uprising in the geologic record, we see kingdom Monera, kingdom Protista, kingdom Animalia, kingdom fungi, and then kingdom Plantae. So the order of uprising is different than the order of complexity. So what is kingdom fungi? This is going to be considered to be the most diverse kingdom of eukaryotes, remembering that eukaryotes are a true cell, and so they have organized DNA, different than a prokaryote, which is simpler. And the beautiful thing about kingdom fungi is that they are able to grow pretty much on any surface that has a mineralogy. So, and even today, like if you see an exposure of bedrock of continental crust that is typically granitic, right? So it's got quartz and potassium feldspar and biotite in it, and we know that those are all silicates. SiO2 is a root, and then they have a variety of other elements attached to it. And so kingdom fungi is using those elements as fuel, as food sources. So as they're doing that, they're taking in those nutrients. They are also breaking down the bedrock. And that's going to be a really useful thing, because although the complexity of fungi are pretty simple, they don't need to grow vertically. Instead, they grow laterally. And so they develop these mats that are called mycorrhizal roots. And so it's a lateral breakdown. And so because those root systems are so close to the surface, they can receive precipitation simply from the atmosphere. So usually there's always some percentage of humidity in the atmosphere. And so it doesn't necessarily have to rain for them to be abundant. So they're really super efficient in their usage of the resources around them. And because these roots are growing laterally, they're going to aid in the nutrient transfer from primitive soil. And essentially, again, this is kind of like a positive feedback cycle, because once you begin to develop these kingdom fungi, they're going to break down that bedrock and eventually produce soil. So the picture on top is of something that's called a lichen that you probably have seen growing on rock, and it is a living organism, and it is growing laterally, and it is using the nutrients within those rocks to be able to sustain itself. The picture on the bottom is of Iceland, where in Iceland you can find these mosses that are anywhere from 2 foot, 3 foot, 4 foot thick, and they will eventually turn into soil units. And so that's the key thing that I want you to recognize here, is that when you have bedrock, you have to have kingdom fungi and then eventually kingdom Plantae to break down that rock, and eventually that rock will turn into soil. So that's where soil originates. It's from bedrock. And when we think about the different type of soil, even like throughout the United States or even throughout the state, it's different based on the type of bedrock that you have initially. So if you have a granite, that breaks down into something called a saprolite. If you have a limestone, that breaks down into a soil that's going to be more calcium rich. So it's important for things like agriculture to know what your bedrock is for growing purposes. And here's a soil profile, and I include this in our geology class because you might not be able to see it in other places, especially if you're a non-major. So it just demonstrates what I just suggested. So you can have bedrock, and that's your original, maybe it's granitic. It breaks down over time into these different layers. So depending on how long the bedrock has been exposed can determine how thick these units are. And usually all of them have some sort of organic layer that is close enough to the surface, unless it's been removed. Okay, so quickly after kingdom fungi becomes in place, you start to have the initiation of the breakdown of the bedrock into soil. And once you have some soil, you can produce a non-vascular plant. So we start to see the initial formations of Kingdom Plantae. A difference in between a vascular plant and a non-vascular plant is the complexity. So those that are non-vascular do have a horizontal rigid stem. However, these are usually more like spore-bearing types of plants, and so they're tied to water in order to reproduce. So they really are not good at preventing desiccation. They have something that's called a hyphaea, and a hyphaea is used because these plants, Kingdom Plantae, is photosynthetic, and so they're taking in carbon dioxide and they're respiring oxygen, and so that hyphaea is able to regulate how much carbon dioxide and how much oxygen is released. But there's going to be a better development of that called a stomata with a vascular plant. So these non-vascular plants are not going to be able to grow very tall. They're going to, similar to Kingdom Fungi, they're going to be more lateral. Mosses, again, are an example of that. This is another picture of Iceland where you see these mosses. And again, they're growing laterally and not so much vertically. So as we move forward, we have non-vascular plants and then we have vascular plants. And the beauty of a vascular plant is that they do in fact have a rigid horizontal system that's going to allow them to transport water. Also, they have a system that's called phloem and xylem. And so it is essentially a means to transport water to the extremities of the plant and to transport nutrients. So you end up with this like circulatory system transporting nutrients and water throughout the system. And so this is a great advancement because this is going to allow for these plants to grow to be much taller. And as we think about that and think about developing this ecosystem on land, we're thinking in terms of Kingdom Plantae being and opening up a brand new ecological niche. So before we were so focused on developing the water column in those shallow marine environments, and we did that with, first stromatolites, and then we had the brachiopods and bryozoans that were able to make a habitat, and that's what we're doing here. So places for other things in Kingdom Animalia to be able to live and protect themselves and use as shelter and also for food. So, Kingdom Plantae is going to be able to have vascular tissue. Additionally, they are going to have cuticles over their leaves, and that's going to help them from desiccation, from drying out. And additionally, with the development of a true stomata that's going to regulate the amount of carbon dioxide in and water and H2O out. So as an example, like usually plants are going to respire after the sun goes down. And that's just to prevent them from losing more water as if they were to open up that stomata during the daytime. So it prevents desiccation. Additionally, vascular plants are going to be able to reproduce without water. So what we're thinking of in terms of branching out and inhabiting all parts of land, even if you're away from a fresh water source or a saltwater source. So these are brand new ideas where we're building up soil for the first time during the Silurian. We're introducing fungi that's helping to break down the soil. And then very quickly, once we introduce non-vascular and then vascular plants, we are more quickly going to be able to break down that soil. And even if we think in terms of that soil is going to provide habitat for other living things. So the vascular plants can reproduce without water, and the leaves are going to help in the photosynthetic process. And the leaves can grow to be much bigger because of the complexity of the phloem and the xylem that provides them nutrients. So it works as a positive feedback cycle as well. One of the common types of vascular plants that we see in the Silurian is going to be a lycospid. And a lycospid is a tree that's going to grow to be about 100 feet. If you look at the picture, it kind of looks like a palm tree. But you can imagine that very quickly in the Silurian, we've gone from these ground-dwelling kingdom fungi to these plants that have root and vascular systems to 100 feet tall. So it's a huge advancement. And typically we find these types of plants in wetlands. So you can look for that diamond-shaped bark. And what you can notice even by looking at the picture, the root system isn't going to be so deep, and that's because there's not so much soil that's produced initially in the Silurian, but they're going to begin to grow laterally. So lycospids are the primary tree source and habitat that's going to be on land. When we think in terms of plant lives, then, just as we did when we talked about the Cambrian explosion, the Cambrian explosion is to water that the Silurian is to land. So we're seeing this process of adaptive radiation. So all of these plants are going to take hold in a variety of different ecological niches. And so we see a quick and steady diversification of the plants once we've established these kingdoms. So once we have vascular tissue, we can see a wide range of different types of plants. And as you know, when we look for plants in the fossil record, we are looking for them. If it's a woody-based thing, then we could certainly look for petrification, but we can also look for impressions and carbonization. And that's really how we have such a good handle on the establishment of these two kingdoms. So the next thing that's going to happen is we're going to see the development of our phyla arthropod that also begins to explode. So you'll remember in the Cambrian we established Phylum Arthropoda when we talked about trilobite. Here we start to see Phylum Arthropoda explode on land. So we're seeing on land versions of those things. So in the fossil record we start to find the very first scorpions and spiders and millipedes, and that's fantastic because these are invertebrates that are on land, and they are essentially what building up this new food web in this new ecological niche. So the Silurian is very much an explosion of life on land, starting with Kingdom Fungi, Kingdom Plantae, and then the arthropods. Some of the millipedes that they find are quite massive. So anywhere from like 2 feet to 3 feet long. I don't know if you've ever seen a millipede, but they're terrifying. In Africa, they cook them, they eat them on a stick. I've tasted it. It's not good. It's not bad, I suppose. It's not good. So that kind of summarizes the Silurian. So it's kind of a big deal because we've seen the uprising of the final two kingdoms, and we're starting to see growth on land. In our next upcoming lectures, we're going to talk about the Devonian, which is going to be the age of fishes. It is a hefty geologic period, so I'm going to stop here, and I'm going to talk about the Devonian all in one separate lecture. So have a great day, and I can't wait to talk to you guys again.